see if they can convince us that their explanation is actually close to the reality. In the paper, they in fact consider the effect of caching and how you lay out your tree in the memory. So if you have a binary search tree, let me go back again to last slide, Gert's slides. There are many different ways that you could lay out this tree inside the memory. So let me just go to the pictures. So for example, if you have a tree like this, obviously this tree needs to be in memory in some order. In which order do you put these elements? There are many different choices for this, and each choice will have its own cache behavior. And they actually do this analysis in the paper to see for a particular way of putting down the tree in the memory, how many cache misses do we expect to see, also given a particular skewedness parameter. Again, this part will require a little bit of theory and to be able to argue for the behavior of an algorithm from a theoretical point of view. But it is important that we take into account this thing, because the way you lay out a tree actually has a big impact on how well it performs in practice. Without considering how a tree is laid out, one could make an objection that it is not the branch prediction that causes this divergence from the divergence of theory with practice. It's just that we have not paid attention to a parameter that influences running time, and that is the layout of the tree. By fixing the layout of the tree and having experiments on the same layout but for different values of skewedness, they can actually show a more convincing evidence that their analysis is correct. So this is again something very important to do, to find all the parameters that could be affecting the runtime, even parameters that are not so obvious. The way you lay out a tree might not be a very obvious thing for you to pay attention to, but of course for a researcher that has been working in this area, it's one of the kind of obvious ones to pay attention to. Okay. Again, so in the paper there is a huge discussion of how you lay out, let's say, random BFS in order, DFSL, etc., etc. Right? I'm going to skip those two things, even though they carefully analyze the behavior of each layout in the memory. So let's go to the experiments and to see if all this theory is actually holds. And in this paper, they also do something else that I really like, and that is they explain very carefully their experimental setup. This is very important when you want to run an experiment, because the reader needs to know exactly how this thing is done, how you collected your experiment. So like they explain here that they use iterative searching procedure. They create a large number of successful queries and measure the running time, and they measure the number of comparisons. So again, that counts, that checks out the second or I don't know, fourth bulletin in my slide that says you need to have a counter. Here they count the number of comparisons, and to do that you can count it in your code. So to count the number of comparisons, you need to put a counter in your code that counts that, which is a software counter. So that's very important. And the number of branch predictions and the number of cache misses or L1 cache misses. And most importantly, they do the experiments on two different machines. You have machine 1, which is, I guess, an Intel, a Pentium 4 running Linux, and the other one is an AMD machine running a different version of Linux. Yeah, which is an interesting to do because you have two different architecture. You have a CPU designed by Intel, you have a CPU designed by AMD. If the two results are consistent, that actually gives more strength to your theory. It makes it stand out better. They also mention how they measure the number of branch mispredictions. They say that they measured branch misprediction using this popular library. I think it's a library that uses hardware counters for this. So that's also nice to know. They also mention their optimization level, and they claim that the result, they're going to show only the results for the AMD architecture because the Intel results were similar. And they also tell us where you can find the source code, even though I don't think this website exists anymore because it's quite a few years ago. Okay. So this is what I really like. To explain how this experimental setup is done, it leaves very little questions to me, and I can't find any major faults here. So let's move on. They also give us their source code for searching. Obviously, searching searching algorithm in a binary search is very simple. You have a key. If it's equal to the root, you return the root. If it's bigger, you go right. If it's smaller, you go left, right? So that's a very easy thing. Then let's move on to how they perform their experiments. So here that they in figure 3, they count the number of comparisons and the number of branch mispredictions. They say that they have a fixed tree of size 25 kilobytes or 25K, and they have 10 to the 6 queries. Important thing about these experiments is that remember that what is it that we want to change or vary in these comparisons? We want to change the skewedness of the tree. So we keep the same elements, we just build different trees. So the figure that we're going to look at does not have on its x-axis n, because n is not what we're interested in. We are interested in alpha. Okay, so that's also another twist that is unusual, because typically you change the number of inputs in your experiments. Okay. And then they say that branch mispredictions could actually go down by a large factor when you change its skewedness, which again is something with consistent with what their theoretical analysis says, and it's also consistent with what they expect. If most of the branches go to one left, then the predictor it's easier for the hardware to predict, because modern computers or modern CPUs are very good in detecting repetitive behavior and adapting to it. So if you have a code, so let me go back here. If you have a code and it's most of this execution of the code, for example, this thing happens, then the CPU will actually learn this and will try to guess most often that it is this branch that is taken by the code. So therefore, if the tree is very skewed, we expect the number of branch misprediction to go down, because the CPU will most often predict that you go to the right. Okay, so it will learn that actually. Okay, so let's look at the results of the experiments. We have the comparisons here. So the comparisons are consistent with what theory predicts. It's basically the same shape. And predictions are also consistent with the theory. At the middle point where the tree is balanced, so this is perfectly balanced tree, you have maximum mispredictions. As the skewness goes down order this way, the number of mispredictions goes down, and it's easier for the hardware to detect, to figure out what's going on here. But of course, we're not here for this. We're here for the running time. So what happens to the running time? Well, the running time is actually slightly more complicated, because they have taken into account different layouts, how you can lay out the tree. And we can see that there are some layouts that are actually not very sensitive towards skewedness. For example, random layout given by these boxes. It's essentially a curve like this that is best when you have a perfectly balanced tree. But there are some layouts, let's say this one, that is kind of goes like this. So in this case, you need to have slight skewedness. And there are some other layouts that, okay, so you can see that there's actually effect of layout. And when we look at cache misses, we don't see a very concrete picture of what's going on here, because the runtime, the cache misses do not seem to explain the running time in all of the experiments here. Yeah, and then there's more here. So, okay, what is this? Yeah, so this is again more comprehensive study of cache misses versus running time. As we can see here, this behavior that the picture looks like this is not explained by the cache misses. So that's a more convincing argument that the analysis here, or the theory here, or hypothesis here is correct. And that's pretty much, this is what I want about this paper. So this is a very convincing argument. And what we can take from this paper, let me just go back to this picture, is that there was a cost associated with cache mispredictions, and you get lower costs if you go either this way or this way. But there's also costs associated with going this way or this way. And at some point, these two things will balance out. There will be a point, for example, at this side, where you have skewness as this parameter, you will achieve essentially a balance between the extra comparisons that you do, but fewer mispredictions that the hardware does. And that's actually a very interesting lesson. And if you're curious, the results of this paper or also other similar papers were replicated. For example, there is studies of quicksort that shows that if you don't pick the median element, the quicksort might actually be faster. Maybe instead of picking a median, pick an element that is among the 10% smallest elements. So your quicksort has skewed recursion tree in it. And again, the experiments are similar. Again, this is a nice example that shows how we can bridge the gap between theory and practice by coming up with an alternative explanation, justifying it from a theoretical point of view, as well as justifying it from an experimental